enough time, so I think I'm going to start. I'm talking today about a project I did while I was still a grad student in Rich Linsky's lab, using invasion experiments to test for ecological interactions within experimental evolution. This was a project done in collaboration with Caroline Turner, also a grad student at the time, also now a postdoc and no longer a grad student. Daniel Mitchell, who was an undergrad in the lab at the time. Rich is obviously an important person to thank, and Nirja, our lab manager / technician, who keeps us supplied with glassware, otherwise we couldn't do anything. So ecological interactions are ubiquitous in nature. This is one of my favorite examples. It's the introduction of wolves back into the Yellowstone ecosystem. Turns out that adding in a top-level carnivore drastically increases the amount of standing biomass of the plant life here, because when you don't have the predators there, the herbivore density is limited primarily by their supply of food. When you put the predators back in, the herbivore density is limited by the amount of them that are being eaten by the carnivores. In response, you end up with much more standing plant biomass. So you get these complex ecological interactions across a wide variety of individuals. These same sorts of things also happen in the microscale instead of the macroscale. And biofilms are really an example of microbial ecology, where you have large numbers of different embedded species, all having their own specialized roles and having complex interactions among them. However, when you're dealing with either of these sorts of systems, it's very hard to understand what is driving some of the ecological interactions, because these are complex ecologies that have evolved for millions or billions of years with many different diverse actors. So in that sense, it can be much easier to start with a simplified system where you know that the diversity you see within the system has all arisen within the experiment. And as such, we've turned to experimental evolution. Because this was in the Linsky lab, like most people there, we were working with the long-term lines. This is a well-known example of experimental evolution. We have 12 independent populations, all originally derived from a single common ancestor, growing in a very simplified environment, in fact, partially designed to limit the role of ecology in here. That doesn't mean that we managed to do that. There are lots of ecological interactions within many of the different populations. And we know of several cases of complex ecologies within populations. Most famously, here in the Aromine-3 population, where we have a coexistence for thousands of generations between individuals that can utilize citrate and those which can't. But there are known ecological interactions within some of the other populations as well. However, most of these ecological interactions that we've uncovered have been ones that have been fortunately linked to observable phenotypes. And we didn't do a systematic screen for these sorts of interactions in the past. So we decided to see what we could do about figuring out what sort of ecological interactions might exist among our populations in a much more systematic way. So the basic approach we took was we used fitness data to predict which populations would be able to invade which other populations when started out as very rare, and then saw if we could use the deviations from our predictions to find ecologies within or between these populations. So the data we used for predictions is all stuff from a paper from a few years ago, where we had taken 6 independent measurements of each one of the populations against a common clone at either 40 or 50,000 generations. All the invasions I will be talking to you today all come from the 50,000 generation populations. We used all of the ones that are capable of metabolizing the sugar arabinose to use as potential invaders, just because methodologically it's much easier to find rare sugar plus versions than rare sugar minus versions. So when we set up our initial screening, I have a couple of graphs here that's easier to just go through the axes. Here on the x-axis, we're plotting the predicted relative fitness of the invader. So when it's above 1, you're expecting to see an invasion. When it's less than 1, you're expecting not to see an invasion. Similarly, here on the y-axis, we have what is a form of the slope of the population size over time of the invader. So when the slope is positive, you're seeing a successful invasion. When the slope is negative, you are not seeing an invasion. This combination essentially sets up a graphical version of a contingency table, where we expect most populations to either be down here where we predict they can't invade, and in fact they can't, or we predict that they can invade, and in fact they can. We then plot our invasions on top of this, and you can see that in general, fitness is actually very predictive of invasion capability. The error bars I have on here on the x-axis are 95% confidence intervals from the bootstrap from the prediction data. On the y-axis, we only ran 3 replicates of each individual invasion, so I've instead color-coded them. The solid symbols are all 3 of the invasions were in the same direction. The open ones are we had 2 in one direction, 1 in the other direction. So there's a certain degree of stochasticity there. So you can see that in general, our predictions make a lot of sense. We have most things down here in the lower left or in the upper right. If you care about stats, I can give you stats that, yes, in fact, fitness is a fairly good predictor at this. But we have a couple of interesting cases. So we have these 2 cases up here where our prediction confidence interval does not overlap 1. So we confidently predict that they are not able to invade. And all 3 of our replicate experiments showed invasion. So these are cases where we think there might be interesting ecological interactions going on. We decide to screen these cases for negative frequency dependence, because any example of negative frequency dependence is itself evidence of an ecological interaction. Because the only difference when you start things at different frequencies is how common that is in the population, and therefore who it's interacting with. So if we go through and test these, we tried them starting the competitions at a variety of different frequencies. So starting out from either 1-to-1 ratios all the way down to 1 to 10,000 ratios. And as a note, these are the ratios we essentially use when making the predictions. These are the ratios we used when we were actually setting up the invasions. You can see in this case we have a very clear example of negative frequency dependence. Fitness is obviously larger than 1 when it's really rare. It becomes statistically indistinguishable from 1 when it becomes relatively more common. But even that relatively more common is still not very common. This is 1% of the population. This is 1/10 of 1% of the population. So the most likely equilibrium point here comes when it's so rare that you still wouldn't be able to accurately pick it up from deep sequencing of a population. Again, if you care about stats, I can show you that yes, in fact, there is a significant pattern here. The other case is slightly more ambiguous. You can see that we have this general trend of higher fitness when rare, coming down to indistinguishable from 1 when common. I haven't decided on the proper form of stat to do across this whole range, but when doing simply a t-test of comparison between the extremes, this one also turns out to be significant, that we have greater fitness when it's rare than when it's common. So these are 2 cases of frequency dependence we did not previously know about. It is possible that one of them may be driven by a known issue of frequency dependence within one of the 2 relevant populations. The other one, neither of the 2 individual populations are known to have frequency-dependent interactions in them, and therefore we have clearly uncovered 1 new case at least. Our general conclusions is that fitness is in fact a good predictor of invasion. So if you can accurately assay the fitness of multiple different populations of the same organism, you have a decent chance of being able to tell which ones are capable of invading the others. But you can use deviations of this to screen for ecologies in a much more systematic way than we've done in the past. We have at least 1 new case of frequency dependence, and possibly 2. And we have this equilibrium when it's still very rare, so these are the sorts of equilibria we would not be able to easily detect with other methods. And this is potentially extensible to other systems, so long as you have the capability of accurately measuring fitness across multiple different subpopulations. And with that, I have plenty of time for some questions.